All right, lecture 35, examples of means of samples. I'm going to work a few problems here. So recall, we know that if x, which I think of as a random variable or as just representing an arbitrary point grabbed from a population of data, right? So if the population of data is normally distributed with mean, mu, and standard deviation sigma, then what do I say? I say for samples of size n, x bar, the mean is normally distributed with mean, mu, and standard deviation sigma over the square root of n. Okay, well, now that you understand that, then anything that you're able to do with just an arbitrary arbitrary normal random variable, such as finding probabilities or areas or finding certain data values that have areas from one side or the other, you know how to do that by converting to z-scores, right? Well, anything you can do there, you can do here as well. It's just this is the new standard deviation you use, right? So I just want to run through a few examples here. So number one, I say, or so my example, I guess, is that according to TalkStats.com, the mean weight of newborns in the U.S. is 7.5 pounds with a standard deviation of 1.25 pounds. Number one, find the probability that a newborn chosen at random in the U.S. weighs within a half pound of the mean weight for all such newborns. And so what does that mean? Well, I would start off by saying if B is the weight in pounds of a randomly chosen newborn, then what we're saying is, so I should call this example, but I'm not going to write all that out. All right. I'm just going to say that B, if that's the weight of a randomly chosen newborn, that generates a data set that generates a population that is normally distributed with mean 7.5 and standard deviation 1.25 in pounds, right? Okay. All right, so what do we want? We want to find the probability that a randomly chosen newborn will be within a half pound of the mean weight of all newborns. So don't we want this? We want the probability that B lies between two values, so it's no more than a half pound below the mean or half a pound above. So isn't this what I want? The probability that the weight of a randomly chosen newborn is between 7 and 8 pounds, right? Okay, and of course, all I'm going to do, we've done this sort of problem before, I'm going to convert to a z-score. And I guess, let's see, maybe what I'll do is, I'll put the picture up right here. Put the picture up right here. So, yeah, let me just do it like this. I guess I probably have enough room. So here's 7.5 pounds, right? And here is my here's my curve, and there's 1.25. I don't think I'm going to write all that in because I'm going to clutter things up a little too much. I'm just going to say this is B. Okay. Well, what I'm going to do is I'm going to convert to a z-score. So I'm going to convert it down to something that will be in terms of the normal 0, 1 random variable, right? And what I know here is that, let's see, yeah, let me write down then, I guess. I want the area. What area do I want? I want the area between 7 and 8. Right, I want that area. So equals this area. And notice when I write with pink, sometimes you can't see it if I stand behind it. All right, so I'm trying to get that area. What does that correspond to down here? It corresponds to some area down here as well, and we get that by converting. So let's just do it right here. The probability that 7 is less than B is less than 8 is, I run through my transformation. I do 7 minus the mean and divide by the standard deviation. less than b minus the mean divided by the standard deviation. This is old hat. You should have this already done, right? You should have paused me and done this. 8 minus the mean divided by the standard deviation. Sometimes, like I said, it goes without saying, I believe, that you should just know to pause me and work the problem. Okay, so we end up with the probability that this is a negative half over 1.25, and it ends up being negative 0.4, less than, this becomes z, and this becomes positive 0.4, correct? So that corresponds to negative 0.4 and positive 0.4. It corresponds to this area. It's the same area. Doesn't look like it, but I didn't draw things to the same scale, right? That's the same area. That's what we want. And that is the probability of that z, and you know how to work this, z less than 0.4 minus the probability that z is less than negative 0.4. And we look all that stuff up, and we get, you should be able to get that easily from your table, 0.6544 minus 0.3466 equals 0.3108. There's the answer. The probability that a newborn drawn at random will weigh between 7 and 8 pounds, within a half pound of the mean of 7.5, is 0.3108. Said another way, 31.08% of all newborns lie within 1/2 of the mean of 7.5 pounds. Okay, now let's contrast this with the next one. The next one says, now suppose we're going to draw a simple random sample of size n equal 25 newborns in the U.S. What is the probability that the mean weight of this sample will be within 1/2 of a pound of the population mean of 7.5 pounds? I'm now interested in the mean weight. So I have a new random variable. I have a new population of data. And that random variable or population of data is normal with the same mean. And the standard deviation is 1.25 divided by the original standard deviation divided by the square root of the sample size. Because sample size, equals 25. And that turns out to be B bar is normal. 7.5 comma, if you work that through, you're dividing by 5, right? So you end up getting 0.25. Smaller standard deviation, okay? And I say that I still want the probability that, that the mean weight will be within 1/2 a pound. So let me kind of draw the analogous picture here. The analogous picture has me with 7.5 pounds here, but now the curve, of course, is much tighter and maybe a little exaggerated, but oh well. And let's see. I want the probability now that I'm within 7 and 8 pounds. So it's the same question, really, and that's the area that I want, correct? What does that correspond to when I convert to the z random variable, though? The z random variable, well, let's figure it out. Let's compute. The probability, and I guess I have room right here, the probability that 7 is less than b hat is less than 8 is equal to, I need to convert to z-scores, so I will make it be 7 minus 7. You know, I'm going to run out of room. Let me try to go where I have a little more room here. I think I have a little more room maybe right here. So this is equal to the probability that 7 minus 7.5 over the new standard deviation, 0.25, is less than b bar minus 7.5 over 0.25, which is less than, can I squeeze this in? 8 minus 7.5 over 0.25. Apologize for scrunching it. But that becomes the probability of, if you work all this through, it's -2 less than z less than 2. So the same region on the number line between 7 and 8 here and 7 and 8 here corresponds to, in terms of area, a much larger region here than here. It's between -0.4 and 0.4 here, and here it's between -2 and 2. So this becomes, same area again. All right? And when we compute that, we get probability z less than 2 minus the probability z less than -2, and that works out to be 0.9772 minus 0.0228, so it works out to be 0.9546. And doesn't that make sense? Whereas if I'm just talking about one newborn chosen at random, the probability's about 31% that they'll be within half a pound. But if I take 25 newborns at random and take their mean, those values should cluster a lot closer to the mean of 7.5 for the population, and the probability that it does cluster within a half a pound is 95.5%, a lot more than the 31% for just one child or one newborn at a time. Okay, that's what's happening. Each time you compute, I have a different standard deviation, so when I compute the probability, it turns into the same area for the z-score, and you can see when the standard deviation is smaller, that same interval gives me a bigger interval on for the z-random variable, which means I'm just going to get a bigger probability. Okay, I filled up the whole board with the first example, but I'm not going to draw pictures for the others, I don't think. That kind of serves as the picture for kind of the model for how to think about things graphically. So I think the others we can do maybe fairly quickly. So why don't you read the next example about the lifespans of pet mice? All right, because what we're going to do there is, it's just a slightly different. It's really not any different, I guess, but it's just worded a little differently, and I did that on purpose. So read through while I erase. Excuse me. Okay, so the plan is Joe's going to buy a baby pet mouse, keep it till it dies, buy another one, keep it till it dies, etc. Do that 4 times, and then he's going to move on to pet lizards. The question is, so the lifespan of mice, these mice in months, is normal 18.3. The mean is 18 months, and the standard deviation is about 3 months. All right. Assuming that, so what's going on then? He has the mouse, dies, then he has another one. He has a total of 4 mice, and the question is, then he's going to go to pet lizards. What's the probability that he will be going to pet lizards in 7 years or less? Okay, well, that means the sum total of the 4 mice lifespan had to be 7 years or less. And what we're really saying then is that the mean lifespan is 7/4 or 1.75 years or less, which is 21 months or less. All right, so what we really want is, I think like this. I think I have a sample of size 4, and if we assume it's a simple random sample, SRS, simple random sample of size 4, then L bar, the mean lifespan, will be the same, have the same mean, and it'll be 3 over the square root of 4. So it's normal with 18 months, and it's going to be 3/2 or 1.5 months. Standard deviation is 1.5 months. Okay? And the question is, if the sum total of these 4 mice lifespans is going to be 7 years or less, what we're really saying is the mean will have to be 7/4 a year or less, or 1.75 years or less, which is 21 months. So what we want we want the probability, and I hope at some point you've stopped me and gone on and figured this out, right? But we want the probability that L bar is less than 21, right? The mean is less than 1 3/4 years, which is 21 months. And you should be able to work that through and get, well, okay, let me do it one more time, because how do I do this? It's L bar minus its mean, which is right there, 18, same as it is there, divided by its standard deviation, which is 1.5, less than 21 minus 18 divided by 1.5, and you work that all out and you get the probability of Z less than 2. 2 keeps coming up, but it's just easy to do the calculations, I guess, with 2. So the answer turns out to be, from the table, 0.9772. So almost 98% probability that within 7 years, he's going to be moving on to pet lizards. Isn't that enlightening? Okay, next one. I want to do one where we start with areas and we find the appropriate data value. Okay, so that's going backwards. We've already done that, so there shouldn't be any surprises here. It's just that we have to keep in mind that the normal random variable we're working with is the one where we get after we divide by the square root of the sample size, right? The standard deviation becomes what we get when we divide by the square root of the sample size. So you should, while I'm erasing, you should zip through that problem. Actually, I guess I'm not quite there yet. Forgive me. It's looks like I skipped a whole problem. Maybe I'll come back and do that one. Sorry, I skipped a problem at the top of page 2. I jumped all the way down to the pet mice problem. Tell you what, maybe I will let you work that one through. Let me just go back up and look at that. Let's see. Talkstats.com also says that a U.S. newborn is considered to be of low birth weight if it weighs less than 5.5 pounds. What fraction of all U.S. newborns are of low birth weight? I will just tell you the answer there is 0.0548. You should be able to get that all on your own. And number 2, would it be highly unusual if the mean of 25 randomly chosen U.S. newborns was below 5.5 pounds? If you work it out, you get a Z-score of -8. And most charts don't even go past -3.5. They give you a probability out there of 0.0001, or I don't know. By the time you get to -8, you got a lot of zeros before you get to a non-zero digit. So it would be an extremely unusual thing, an extremely unusual event to have a mean of 25 randomly chosen newborns to have a mean weight of 5.5 pounds or less. All right, that's all I'm going to do on that one. I want to go to this last one here while we still have a little bit of time. Okay, so using the lifespan of mice information from the previous problem, let's say that any mouse whose lifespan falls in the lowest 1.5% of mice lifespans is unusually short-lived. Find the age in months that is the cutoff age below which a mouse is considered unusually short-lived. All right, so I know that my sorry about the squeaks. I guess it's appropriate for a mouse problem. I know that my lifespan for mice is normally distributed with 18 months mean and 3 months standard deviation. Let me just draw the curve here a little to make sure you know what we're talking about. Here's 18, and I won't draw on the standard deviation again. What I want to do is I want to find the L value back here so that the cutoff, so that the probability, I'm going to find the cutoff L value here so that this is 3%. So if a mouse only lives to be this long or less, it's 0.015. Sorry, 0.015. I want to find this value. So really it's, well, let me just go ahead and say, well, it's a cutoff value. I'll just write it in when we get it. But if a mice lives this long or less, they're in the bottom 1.5%. Okay, well, you know what to do. First, pause me and do it. First, do the z-score. So I have my z-score here. This is z, and I go back and I find 0.015, and the z-score you should get is negative 2.17. All right. So what's the mouse value here? The mouse lifespan value. L is equal to, you remember what you do? You do mu plus the z-score times sigma. So we get 18 plus negative 2.17 times 3, and you work that out and you get 11.49 months. So about 11 and a half months. If a mouse lives 11 and a half months or less, they're in the lower 1.5% of mouse lifespans. Now suppose the cutoff age for the mean lifespan of a simple random sample of suppose we want to know the cutoff age in months for the mean lifespan of a simple random sample of 16 mice in order for it to be considered unusually short. We are keeping the same criterion that the mean lifespan must fall in the lowest 1.5%. All right, we have n equals 16, so the new random variable we're looking at is the mean lifespan. It is normally distributed with the same mean and standard deviation, the original divided by the square root of 16, right? You got that, right? So it's 18 and 3/4, or 0.75. I want to do the same picture here, only I have this up here was for L, and this is for L bar, and it's, here's 18, and it's just a lot more scrunched and humped up, right? And I'm back here, the same place, and there's, 1.5%. I'll just call it that. And I'm going to leave you to work it out. And actually, I've written a little bit, maybe a little bit misleading, because, the tail drops off so fast. So it's up here a little bit closer, isn't it? That's the point. This area is so tiny until I get right up to it, and then the area humps up, right? Because that standard deviation pulls so much in. So work through. Don't just write the answer, and you get 16.3725, right? So let's just say we're all done, 16.4 months. So that's what goes right there. All right, and again, that should make sense that you scoot in pretty close and you only have 1.5% of the area, because the probability of the area is scrunched in so much more closer when I'm looking at a mean. When I'm looking at the original random variable or the original data, it's spread out more, and so I'm out here farther, and this farther away. This turned out to be 11.49. It's farther away from 18 than this 16.4 is, right? Pretty neat.